So we can see some questions like, what is seismic design? Seismic design is the process of designing buildings and structures to resist the forces generated by earthquakes. It's nothing but there are forces generated by earthquake process. So we need to design the building and structures to to withstand these forces generated by earthquake. So that process is called seismic design. It involves understanding the behavior of structures under dynamic loads, including vibrations, and ensuring that they are strong enough to survive earthquake-induced forces without collapsing and sustaining excessive damage. So in this process, like in this design process, we need to understand how the dynamic loads are behaving and how the vibration patterns are happening, and then how the structure is strong so that it can survive and withstand those earthquake-induced forces. The structure should not collapse, or even the major part of the structure should not have any excessive damage. That's what we need to design. So that's the whole process called seismic design. Why is it important to understand the vibration behavior of the buildings? So the question is like, why we need to understand why is it important to understand the vibration behavior of the buildings? So by understanding the vibration behavior of the buildings, we can design the structure safely. So understanding vibration behavior is it's crucial, because during an earthquake, the structures experience dynamic forces. So there are dynamic forces that will be applied to the structure during the earthquake analysis. So if these forces are not accounted for the design, if you don't account for it, what would happen? Then they can cause structural failure. If you don't design the structure for those forces, then the structure cannot withstand those forces, and it will not be safe. And moreover, the structure will, when it's getting exposed to this kind of earthquake, then it will fail. So we need to design the structure safely. So we need to understand how the vibration behavior of the buildings are there. By studying the vibration patterns, engineers can ensure that buildings are designed to withstand forces and keeping occupants safe. The safety is almost paramount. That's why we need to understand the vibration behavior of the buildings. So what are the three main questions in seismic design? So what are the three main things, main important things we need to study in seismic design? There are three main questions. How does the building vibrate? That's related to the modal shape. How does the building vibrate? How fast does the building vibrate? And it's related to the modal period, and how much mass participates in the vibration. How much mass of the building or structure participates in the vibration. That's related to the modal mass. So what is modal shape? The modal shape is a deformation pattern in which structure naturally vibrates when subject to dynamic force. When the structure is subject to the dynamic force, it will start vibrating again. That's natural vibration. How the deformation pattern is happening. That's the thing we call as a mode shape. So each mode shape represents the different pattern of vibration, and the building moves differently depending on which mode is excited. So if the first mode is excited, it will move differently. Second mode is excited, it will move differently. So every mode has its different vibration pattern, different deformation patterns. So it's essentially how the building deforms or bends during an earthquake. So it's nothing but it's how the building deforms or bends. When the earthquake is happening, the building is going to deform and bend, right? So how is it going to bend? How is it going to deform? That study and that kind of thing is related to the modal shape. So modal shape is nothing but a deformation pattern. Why do buildings vibrate in different modes? So we can ask why is it not vibrating only one pattern? It's vibrating in different modes. Why? The buildings vibrate in different modes due to their natural frequencies. Just like guitar string vibrates in different patterns depending on how it's plucked. If you plug the guitar string, it vibrates in different patterns depending on where it's getting plugged, how much it's tightened, all these things. The same way the building vibrates in various patterns modes depending on the shape and size and structural characteristics. There are different characteristics like how it is structural shape and size and characteristics of the structure. Based on that, it vibrates in different patterns. And these modes correspond to natural frequencies at which the building can vibrate. So what happens when the building vibrates in multiple modes? So if the building vibrates in multiple modes, what would happen? In the real world scenarios, the buildings rarely vibrate in one mode. It's very, very rare the building can vibrate only in one mode or only one pattern, only one approach. It's not possible. In real world, it's going to vibrate in multiple modes combined together. So it's creating more complex vibration patterns. So this interaction can lead to unexpected behavior during an earthquake, making it essential to consider all relevant modes in the design to ensure the building can withstand the combined forces. So we need to understand like how the combination is going to occur and how this interaction between these behaviors are happening, and making it essential to consider all relevant modes in our design. So we need to consider all the modes in our design so that we can design the building with that can withstand safely the combined forces. What is modal period? The modal period is the time it takes for the building to complete one cycle of vibration of in a given mode. It's essentially how fast or how slow the building vibrates in that mode. So we can say that if it happens in the first mode, how much time or how fast it's going to vibrate in that particular mode. That study is related to the modal period. The modal period is inversely related to the frequency of the vibration. The longer period, it's slower the vibration. That means it takes more time to complete one cycle. That means vibrating slowly. So it vibrates slowly means it takes more time. If it moves slowly, it takes more time, right? The same way, like if the structure is having a natural period, first mode it will have more period. That means it's moving slowly. The higher modes, higher frequencies, higher modes, it moves very fast. So the frequency is more, but the period will be less. How does the modal period influence the building seismic performance? It's indirectly we are asking like what's the relation between the modal period and seismic performance. The modal period determines how the building responds to seismic waves. A longer modal period means the building vibrates more slowly, while shorter period means it vibrates faster. So shorter period means vibrates faster. More period means it vibrates more slowly. The buildings with longer periods are less responsive to higher frequency earthquake waves. If the higher frequency earthquake waves comes to the structure, it has longer period, then it will be less responsive. While shorter period buildings may be more vulnerable to certain types of ground motion. Why is it the first mode the slowest vibration mode? Why is the first mode slowest vibration mode? Why do we say that the first mode is the slowest vibration mode? Because the first mode represents the building's fundamental frequency, the lowest natural frequency of the vibration. Because the building's structural stiffness, mass distribution, it vibrates more slowly in this mode. Higher modes corresponds to higher frequencies which involve faster vibrations. What is modal mass? Modal mass refers to the amount of mass in the building that participates in a particular mode of vibration. For a particular mode of vibration, how much percentage of mass participates, how much part of the building participates in that particular mode of vibration. In other words, it indicates how much of the structure's total mass moves during each vibration mode. So for example, if it is a fundamental mode, first mode, most of the building it will move together. So that means modal mass will be more participation in case of fundamental vibration. That's the first few vibration modes. So that's important. Like the first mode typically involves most mass, with higher modes involving less mass. So as you go higher modes, that means whatever the vibration makes faster, higher modes, faster vibrations, it will less mass only it will get involved. If it is the slowest mode, that's the first mode, it takes more time, but the more amount of mass of the building it's participating together. How modal mass affect a building's seismic behavior? Modal mass affects the building's ability to resist seismic force. So modal mass affects building's ability to resist seismic force. The more mass involved in a mode, if a particular mode is having a lot of mass, that means a lot of forces the building has to resist. So if the first mode involves most mass, that mode will carry largest portion of the earthquake's energy. That means most of the earthquake's energy is taken by the first mode. Understanding the modal mass helps engineers more efficient and resilient buildings. That way we can design. How modal analysis work in seismic design? Modal analysis is a computational method to determine modal mass, modal shape, and modal period of a building. By simulating how the structure vibrates, engineer can identify its natural frequencies, deformation patterns, and how different parts of the building respond to the seismic forces. This information is crucial for designing the structure that can resist earthquakes. What role does modal analysis play in structural design? Modal analysis helps engineers understand how a building will respond to dynamic loads, including earthquakes. It allows for the identification of the critical vibration modes that need to be addressed during design phase. So we can identify like what are the modes that are critical for the vibration. So we can address during the design phase. Without modal analysis, engineer can't be able to predict how a structure would behave when under seismic forces, which could lead to unsafe design. If we don't study the modal analysis, then we are designing like unsafe design. That's not happen. We need to design always safely. So we need to understand and predict how the structure would behave under seismic forces. What is the relationship between the modal period and building height? Taller buildings generally have longer modal period. If the height of the building is tall, and it will take a lot of time to complete one cycle, so it means like it have a longer modal periods, meaning they vibrate more slowly than shorter buildings. They vibrate more slowly than shorter buildings. This is because the tall structures tend to be more flexible and have greater mass at top, which leads to a slower mode of vibration, slower natural vibrations. Shorter buildings, on the other hand, have stiffer structures, thus vibrate more quickly. How do higher modes of vibration affect the building? Higher modes of vibration correspond to faster, more localized oscillations. Usually the higher modes are more localized oscillations, localized vibrations. These modes may cause certain flows or structural components to vibrate more than others. Although higher modes typically involve less mass, they can still have significant impact for that particular mass of the structure, particular portion of the structure, particularly in taller buildings, where higher modes can lead to differential movements between floors. Why is the first mode the most important in seismic design? The first mode is the most important because it generally involves the most mass, more number of mass, like most of the mass is participating in that first mode and governs the overall response of the building during earthquake. Since it is the slowest and most influential mode, engineers focus on designing buildings to handle this mode effectively to ensure the structure can withstand large amount of force that's going to come, so that the structure will not collapse. So without collapsing, we need to design the structure to resist those forces. What happens if the building's natural frequency matches with earthquake frequency? If the building's natural frequency matches with the frequency of seismic waves, resonance occurs. This can amplify the vibrations within the building, potentially causing severe structural damage, even failure. Engineers must design the buildings with sufficient damping and flexibility to avoid resonance with typical earthquake frequencies. How does damping affect buildings' response to earthquakes? Damping refers to dissipation of energy that occurs when a structure vibrates. The more damping a building has, the less it will sway during earthquake. Proper damping is essential to reduce the amplitude of vibrations and prevent structural damage. Engineers can include damping devices such as shock absorbers to enhance the building's seismic performance. What is the significance of higher modes of shorter buildings? What is the significance of higher modes for shorter buildings? For shorter buildings, higher modes typically have less influence because the building is relatively stiff and does not experience significant displacement in higher modes. However, these modes can still affect the overall seismic behavior, particularly in buildings with irregular shapes and complex load distributions. How are the modal shapes determined during the design process? Modal shapes are determined through modal analysis, which uses computational models to simulate how a building responds to dynamic forces by applying the loads and measuring the resulting deformation. We need to apply the loads and we need to measure how much deformation is happening, so that engineers can calculate natural vibration patterns and ensure the building is designed to resist those forces during earthquake. How do irregularly shaped buildings affect vibration behavior? Irregularly shaped buildings can cause more complex vibration patterns compared to the regular structures. The irregularities can lead to localized concentrations of vibration or cause higher modes to have greater effect. Engineers must account for these irregularities in the modal analysis to ensure the building behaves predictably during an earthquake. What is the difference between the rigid and flexible buildings in the terms of vibration? Rigid buildings are stiff and have a shorter mode period, and meaning they vibrate quickly. Flexible buildings, on the other hand, have a longer periods and vibrate more slowly. The flexibility of the building influences how it responds to seismic force, with flexible buildings tending to sway more, but often dissipating energy better. How do engineers use modal analysis results in practice? Engineers use these results from modal analysis to refine their designs by identifying the modes of vibration that need to be addressed. For example, they may add a reinforcement to the parts of the building that are likely to experience the most stress during an earthquake. Modal analysis also helps engineers to optimize damping and other systems